continue our discussion of the Fourier transform, and we take further the properties of the Fourier transform from the properties that we discussed in the previous lecture. In the previous lecture, we had talked about duality in the context of the Fourier transform, where we had shown that there is a great symmetry between the Fourier transform and the original function, in the sense that if a certain function small x of t had the Fourier transform capital X of omega, then one could obtain the Fourier transform of capital X of t in terms of small x of omega, right. So, there is a match both ways. That means a particular function having a particular Fourier transform means the Fourier transform viewed as a function in time has a similar, has a Fourier transform equal to the original function viewed in frequency, right. We had used that to establish that the Fourier transform of a sin t by t kind of pattern was a rectangular pattern in frequency. Now, the reason why duality becomes important in a lot of situations is that in the absence of duality, it can be extremely difficult to calculate the integral in question. So, it is much harder, for example, to evaluate the inverse of, the Fourier transform of sin t by t directly by integration rather than use duality. Yeah? The same principle would hold good in a number of other examples, and you will continue to encounter such examples as you use your knowledge of signals and systems in a variety of the courses or in a variety of the contexts that follow. For example, in the context of communication, in the context of control, in the context of instrumentation, in the context of analog electronics, and so on. Right? So, duality is a very, very important principle which one needs to appreciate very thoroughly. We had also looked at the effect of time shifting of a function, right. If one shifts a function in time, the effect is to add a linear phase to the Fourier transform. Now, we would like to look at the dual effect. Suppose we shift in frequency. What do we expect? Expect that there will be some kind of modulation in time. But let us get the precise expression. So, we now establish what we call the modulation theorem of the Fourier transform. Assume we have a function xt with Fourier transform x omega. We will assume here that the function is not periodic. Yeah, we assume the function is not periodic. We multiply this function xt by a complex exponential e raised to the power j omega naught t, and we ask what is the effect on the Fourier transform. Well, let us write down the expression for the Fourier transform of this function. So, we have e raised to the power j omega naught t xt e raised to the power minus j omega t dt, and we may write this as xt e raised to the power minus j omega minus omega naught into t dt. So, quite clearly, since this converges, since x omega is convergent, we assume that is the case, this also converges. The only change is to replace omega by omega minus omega 0. So, the effect is to shift the Fourier transform forward by omega naught. The effect of multiplication of the original function by e raised to the power j omega naught t is to shift the original function forward by omega naught. Is that right? So we may write this. So we now fill in the answer here. The answer is x of omega minus omega naught. Needless to say, this can be applied whether omega naught is positive or negative. And therefore, if omega is positive, there is a forward shift. If omega is negative, it is a reverse shift, a backward shift. Now, you notice the use of the word modulation. I thought one should spend a minute or two elucidating the meaning of this word. To modulate, in common parlance, means to change in a pre-decided manner. For example, when I speak and when I want to express something, I modulate my tone. I can modulate my tone with emphasis. I can modulate my tone with a musical note. I can modulate my voice with emotion. Modulate means to change subtly or to modify in a certain pre-decided manner. All right? The word modulation is used in electrical engineering very frequently, particularly in the domain of communication. We say that we modulate a waveform typically when we multiply the waveform by a fixed or pre-decided waveform. As in this case, here we multiply an arbitrary waveform xt by the fixed waveform e raised to the power j omega naught t for a given omega naught. Now, the context in which this is important, as you notice, what happens as a consequence of this? See, when you modulate xt with e raised to the power j omega naught t, the effect is to shift the spectrum forward in frequency. Or the other way to look at it is the effect is to relocate the spectrum. Now, suppose you have a number of different waveforms to be transmitted simultaneously on the same device or on the same channel, on the same wire. And if all the waveforms happen to be in the same spectral region, that means the predominant part of their spectrum, the predominant part in which the Fourier transform has a significant magnitude, right, is all in the same region. Then if we simply add them and transmit them, they would overlap with one another and they would not be separable at the receiver. But if we use this principle to force them to occupy different regions of frequency, then at the receiver, one can extract different parts of the frequency axis and retrieve the original waveforms, although originally they were all in the same band. So this principle is used in communication engineering for transmitting a number of different waveforms, all really in the same band of frequencies over the same channel, by using what is called frequency division multiplexing. Frequency division multiplexing means to put together and transmit in a separable way, right? And frequency division multiplexing means to take the spectrum, divide the spectrum into different frequency ranges, and to put waveforms which are otherwise in the same band in different spectral ranges by using the principle of modulation. We now come to the next property of the Fourier transform, namely what happens when we differentiate. So let's study the effect of differentiation. Now, for this purpose, let us write down not the Fourier transform relationship, but the inverse Fourier transform relationship. So we'll write down x of t is 1 by 2 pi integral over all frequencies capital X of omega e raised to the power j omega t d omega. Our intention is to find out what happens when we differentiate the waveform xt. What happens to the Fourier transform? Yes? So let's differentiate both sides with respect to t. Now we can do that because this integral is on omega. And if the integral is convergent, then under a wide class of conditions, one can also rearrange the ordering of differentiation and integration. We will see that. So, we will first differentiate both sides with respect to t, with respect to time. Clearly, this is 1 by 2 pi. Now view this integral. The integral is on omega. Inside the integral, the integrands have only one term dependent on t, namely e raised to the power j omega t. In a wide class of situations, the integral, the derivative with respect to t can be taken inside the integral sign and operated only on those terms in the integrand which depend on t. And here that is e raised to the power j omega t. So, clearly this would be integral minus infinity to plus infinity x omega right. So, this becomes 1 by 2 pi integral minus infinity to plus infinity j omega times x omega e raised to the power j omega t d omega. So, it is quite clear this of the derivative of xt here. If we look at this expression, this is clearly the inverse Fourier transform of this expression, and therefore, this is the Fourier transform of the derivative. So, let us write down the result here. What are we saying? We are saying that the operation of differentiation in time leads to the operation of multiplication by j omega in frequency. What is the good part about this? The difference, yes? Memoryless, that is correct. An operation like differentiation, which actually is not really memoryless, transforms to a memoryless operation in frequency. Yeah? In fact, it is a local operation. The idea being that the derivative of a sine wave or the derivative of a complex exponential of frequency omega is also a complex exponential of frequency omega, appropriately changed in amplitude and phase. It is changed in amplitude in a manner proportional to the frequency, and it is changed in phase uniformly by 90 degrees. That is interesting. Now, duality tells us something very interesting. It tells us that if I multiply a function by t in time, then I should have an operation similar to differentiation in frequency. Yes? Let us establish that. So, multiplication by t . In fact, here we shall make use of the Fourier transform relationship. So, x omega is minus in infinity to plus infinity x t e raised to the power minus j omega t dt. And now we shall differentiate both sides with respect to omega to yield by the same argument we carry the derivative into the integral sign and get which goes to say that if you multiply xt by minus jt, the effect is to take a derivative in the frequency domain with omega, a derivative with respect to omega. So therefore, by the linearity of the Fourier transform, one can modify this. One can show if you multiply both sides by j, we shall have j times dx omega d omega is the Fourier transform of t times xt. All right, so we summarize this by writing t times xt has the Fourier transform j times dx omega d omega. All right. Of course, the same result can be obtained by duality. If one applies the principle of duality correctly, one would come to the same conclusion. Yeah. Now, the next property of the Fourier transform that we'd like to investigate is the property of scaling of the independent variable. See, we've been scaling the dependent variable. That means, because of the linearity of the Fourier transform, we know that if we multiply a function by a constant, the Fourier transform is also multiplied by a constant. So that's not something very surprising or interesting. But suppose we scale the dependent variable. That means instead of t, we have 2t. So what does it mean? When you replace t by 2t, you're squeezing the function on the time axis. When you replace t by half t, you're stretching the function on the time axis. Or in general, if you multiply the variable t by a real number a, we wish to ask what happens. Of course, it cannot be multiplied by a complex number here because the variable t is assumed to be real. It's not a mapping on the complex numbers. So the signal itself is a mapping on the reals. So we'll assume then that we are multiplying the independent variable by a constant a, which is real. So scaling the independent variable. So what we are saying is, instead of xt, we replace t by at, where a is real. Not necessarily positive, not necessarily positive. Let's evaluate its Fourier transform. We replace at by a different variable lambda, and therefore dt becomes 1 by a d lambda. Now, we also need to make a replacement of the limits accordingly. Now, let us pay attention to the limits here. Now, we will take two different cases, A positive and A negative. Suppose A is positive. When t runs from minus infinity to plus infinity, then at, which is lambda, also runs from minus infinity to plus infinity, so there is no problem. On the other hand, when A is negative, then t runs from minus infinity to plus infinity, means that lambda runs from plus infinity to minus infinity. Alright? But then we have here a 1 by A d lambda replacing dt. And if A is negative, 1 by A is also negative. So there would be a negative, so you see the 1 by A would take a negative sign, this the integral would also get reversed if A is negative. So in general, one may rewrite this in the following way. We may rewrite it as integral minus infinity to plus infinity x lambda e raised to the power minus j. Now in place of t I write lambda by A, so omega by A times lambda. Dt is d lambda, but then we divide by mod A. Care of this. So if we take, if we realize that we can see d lambda by A can be rewritten d lambda by mod, the limits can be kept the same. If A is positive, then of course 1 by mod A is 1 by A. If A is negative, it would be minus 1 by A, and that would take care of the limits also. And therefore, this is nothing but the Fourier transform of x evaluated at omega by A and divided by mod A. Now, it should be noted here, the effect of scaling the independent variable with A, real number, is to multiply the frequency axis, or also scale the frequency axis by 1 by A. And please note that here it is scaled by 1 by A and not 1 by mod A. On the other hand, the whole form is also multiplied by a constant equal to by mod A. So the multiplying constant is 1 by mod A, whereas the scaling constant inside the Fourier transform is 1 by A. Right? This should be carefully noted. So it's interesting, there is a very powerful duality here. The scaling of the independent variable in time also results in the scaling of the independent variable in frequency. Right? With a little change, the Fourier transform is also multiplied by a constant. Right? So scaling the independent variable in time also amounts to effectively scaling the independent variable in frequency and also a multiplication. Yeah, of course, if one wants perfectly symmetry, one scale the independent variable in time and multiply by square root of A. That would be perfectly symmetric. Right? So then one would have a perfectly symmetric relationship. Now, the next principle that we need to derive in the context of the Fourier transform is what happens when we multiply a function by not a complex exponential but a sine wave. So suppose we take xt and multiply it with a carrier. Let's call this a carrier. Cos omega naught t. Yeah? The effect, of course, can be obtained from our knowledge of what happens when you multiply it by a complex exponential, because we can always decompose this into exponentials. So you may rewrite this as half xt e raised to the power j omega naught t plus xt e raised to the power minus j omega naught t. And what is the Fourier transform of this? Half x omega minus omega naught plus x omega plus omega naught. What does it mean? When we multiply xt by a cos function, cos omega naught t, and when would we do it practically? We would do it to transmit. See, all the when you switch on to an amplitude modulated radio, AM radio, that's exactly what they're doing. So at the transmitter end, the music that you hear is actually being multiplied by a cos omega t, right, with an appropriately chosen point t equal to 0. All right. So why do we do it? Well, I was explaining to you that, you see, now firstly, why should we multiply by naught t and why not e raised to the power j naught? Well, that's because e raised to the power j omega naught t is not physically realizable, right? It would be nice to, actually it would be nice if we can multiply by e raised to the power j omega naught t, but that's not physically doable. What it means physically is you're really having two different transmissions of a real part and an imaginary part. Now, why should we multiply at all by a sine wave? That's because it allows you to shift in frequency. So it's like saying, you see, it's like this. See, suppose, I mean, you want to transmit. Think of the process of transmission as sending some luggage on a road, right? There are many parallel roads, 10 parallel roads. If all vehicles insist that they should travel only on the leftmost lane, then it may not be possible, right? I mean, they would all get stuck. They would have to travel in single file. What do you mean by traveling in single file? It means not synchronously, right? So, you know, go. But if there are 10 vehicles and there are 10 roads in parallel, all of them can go in parallel if you allow them to take different roads. That's exactly what we're doing here. Suppose many people want to transmit their music at the same time. By and large, our audio frequencies are in the range 20 hertz to 20 kilohertz. So most songs would have a significant part of the spectrum. See, what do you mean by significant part of the spectrum? That means the part of x omega, that part of the omega axis where mod x omega is significant. If you look at, you know, mod x omega square and look at the part which has the most significant values, that's called the significant part of the spectrum. So you see, in fact, not even 20 kilohertz. Most audio is between, say, about 400 hertz and about 12 kilohertz or 13 kilohertz. It's only singers with a very high pitched voice that can go up to 20 kilohertz, right? So maybe about 10 kilohertz or so is the range of the spectrum. Now, if all people who sing wish to transmit at the same time, so, you know, you want to be able to tune, don't you? I mean, you want sometimes to listen to Lata Mangeshkar, sometimes to listen to Rafi, sometimes, and well, all of them must be singing for you at the same time. Now, this is not possible unless you allow all their songs to travel on different roads. And what do you mean by different roads? Different parts of the frequency axis. Now, how can you put them onto different parts of the frequency axis? By doing this, right? Now, why would you do this as opposed to multiplying? As I said, it would be nice if you could multiply by e raised to the power j omega naught t. But actually, physically, what does it mean? Multiplying by e raised to the power j omega naught t means multiplying by a complex number, which means actually multiplying by two real numbers. So, you're using two channels instead of one. Now, that you're doing here by multiplication by a real number. You're shifting the spectrum forward by omega naught as also backward by omega naught. And you're adding them together. What are you doing when you multiply by cos omega naught t? You're shifting the original spectrum forward by omega naught and backward by omega naught and adding up the two spectra. Is that right? And this is done because you want to transmit the original x omega in a frequency range different from the original frequency range. Yeah, is that clear? Any other questions on why we do this? Now, this is also called, in fact, this is what is more commonly understood. Yes, Samir? How do we get it back? That's a very good question. How do we get it back? Right? All right, since the question has been raised, in fact it's very simple. It's very simple. Yeah. Suppose we any suggestions, the question Samir asks is, now we transmit this. How do we get it back? How do you get it back? When you tune into your AM radio, what are you doing? Yes, yes, Nikhil.
So we are tuning into the higher frequency.
You have to speak into the mic. It's not audible.
So the x of omega, it will have a maxima in the voice range, that is whatever 20 hertz to 20 kilohertz. Now when you're doing this x of omega minus omega naught and plus x of omega plus omega naught, we'll have two maxima at omega plus omega naught also. So now we won't consider omega minus omega naught because there will be a interference with all other signals of the same frequency. We'll consider at omega plus omega naught, and that will be separated by filtering, and from that you can obtain back the signal.
Okay, very good. Good. So the suggestion is that, you know, we, as Nikhil says quite correctly, I mean, suppose x omega is, see, let's take an example. I mean, let me take an example of this, right, to make the point clear. Suppose this is the original spectrum. Suppose, I mean, I'm taking an extreme situation. Suppose we have an x omega that looks like this. So let's say this is omega m, right? This is minus omega m. Okay. Now tell me, for the moment, let's assume the phase is 0, right? For simplicity, let's assume the phase is 0. So the amplitude, I mean the magnitude of the Fourier transform is equal to the Fourier transform. Yeah. Now my first question to you is, why have I drawn a symmetric x omega? Because the signal xt is real, right? If xt is real, its magnitude is symmetric, and if the phase is 0, then it is symmetric. Yeah. Now suppose the frequency omega naught is much larger than omega naught, but much larger than twice omega. Right? So this is called the bandwidth. This is, I mean, this is see, by the way, what I've drawn here is an idealized situation. Idealized means it's, you know, it's not really what practical signals have. Practical signals will always have some tail, right? But we idealize. This is called the bandwidth of the signal. Okay. Now let's assume that omega naught is much greater than 2 times omega m. And we look at what happens to the Fourier transform of xt cos omega naught t. We would like to obtain this graphically. Yeah, graphically. So what would it be? It would be the original spectrum shifted forward by omega naught t and backward by omega naught, by omega naught, not omega naught t, by forward by omega naught, backward by omega naught, multiplied by half and added. Yeah, so it would look like this. So as I said, omega naught is much greater than 2. We have something like this here and something similar here. This point is omega naught plus omega m. This point is omega naught minus omega m. This point is minus omega naught plus omega m, and this point is minus omega naught minus omega m. Is that right? Of course, if the maximum here were 1 unit in the original one, now the maximum would be half. That's a minor point. You can always multiply by 2 times cos omega naught t. It's a minor problem. Right? Now, suppose I multiply this. Now, this is what is transmitted on the channel. This is what is transmitted on the channel. Right? Now, at the receiving end, suppose I multiply this by cos omega naught t again. Right? I multiply this by cos omega naught t again. What would happen? The original spectrum would get shifted forward again by omega naught and backward by omega naught, and these would be added. Yeah? Now you see, just visualize the situation. So what would happen? You see, this is, I mean, let's say this is, this is the front side, the rear side. Let's say front side, rear side. So it's okay. Now, when I shift, when I multiply this by cos omega naught, the whole thing is shifted forward and backward by omega naught. So what happens? This comes, when this is, now when you shift forward, what happens? This comes here, right? So you get, so I mean, let me call this, A, and let me call this B. So I have B, when you shift forward, B comes to 0 frequency. Yeah? So we get this. And of course, front rear is correct. So we get B. And what happens to this? When you shift forward, it goes to 2 omega naught. It goes to 2 omega naught. Now what happens when you shift backwards? This one comes to 0. And this one goes to minus 2 omega naught. Is that right? This one comes to 0, minus 2 omega naught. Is that right? So we have B is the solid one, and A is the dotted one. And of course, front rear match. The front goes on the front and the rear goes on the rear. Is that right? Yes? Now, suppose, you see, now, of course, I am not drawing the ones at 2 omega naught. They are very far away. Now, suppose I put an ideal low-pass filter. Suppose I put an ideal low-pass filter. What should be the cutoff frequency of the low pass filter? Just a little more than omega m. Yeah, just a little more than omega m. And of course, since omega naught is much greater than omega m, 2 omega naught is also much greater than omega m, and 2 omega naught minus omega m is also much greater. So that those other spectra will never interfere with this. So by putting a low pass filter, this can be extracted and the original signal is obtained. Yes, Samir. Yeah.
We have to put a band pass filter in the previous stage, not this stage.
You need to put a band pass filter in the previous stage. Well, you need to put a band pass filter if you are worried that there are other components or other spectra which lie in other bands. Otherwise, you don't need to. That's right. That's right. He's right. He says that we need to put a band pass filter to make sure that, if there are other things in these spectral ranges, then you need to remove them by using a band pass filter. That would be necessary if you think that there are other spectra there. Otherwise, it would not be necessary. I mean, theoretically, in the ideal case, you don't need to. But here you do need to put a low pass filter to extract the original signal. So this is what happens in your AM radio. So what you've just seen is an example of what is called amplitude modulation and amplitude demodulation. This is the principle behind amplitude modulation and amplitude demodulation. Demodulate means the opposite of modulate. Demodulate means to remove the effect of modulation to get back the original signal. So now you know what happens inside your AM radio. Yes? Now, we would like to see the same thing in time. We would like to see the same thing in time. What are we doing in time? You see, modulation is multiplication of xt by cos omega naught t. Demodulation is also multiplication of the modulated signal by cos omega naught t. So we have cos squared omega naught t. Now this can be rewritten as half xt into 1 plus cos 2 omega naught t. Is that right? So we may rewrite this as half xt plus half xt cos 2 omega naught t. Is that right? That's exactly what we saw. When we demodulate, we get back the original signal and also a version of the signal modulated by a carrier of frequency 2 omega naught. What do? We remove this term by passing through a low pass filter. Yeah? But of course, as an additional remark, one may also use this to increase the frequency of the carrier. So the idea of demodulation can also be used to further modulate. And then as Ameya says, instead of putting a low pass filter, if you put a band pass filter around 2 omega naught, you will get the original signal modulated by twice the carrier frequency. Is that right? So you, yeah, you see here we are getting a factor of half because you see, you remember that the original, every time you modulate, you take the original spectrum, shift it forward and backward and multiply by half. But then when you demodulate, these come back to zero frequency and add, but then each of them is again multiplied by half. So you would actually be multiplying by 1/4, but two of them add up with multiplication by 1/4. So you get a multiplication by half. And of course you also get a multiplication by half on the other carrier. Yeah? So much so for amplitude modulation and demodulation. Now we come to the next and a very important property of the Fourier transform, namely the idea of what is called dot product conservation. It's a very deep idea. It's called Parseval's theorem. After the mathematician or scientist Parseval. Now I will first explain the idea behind the theorem. The idea is, you see, you've been noting that there is a close association between Fourier transforms and the idea of dot products between signals. Yes? Now what we are going to show is, if I take two signals and find their dot product, right, then this operation of finding the dot product is valid either in time or in frequency. That means it doesn't matter whether I calculate the dot product of the signals in time or I calculate the dot product of the signals in frequency. What does it mean mathematically? What are we saying? We are saying integral xt y bar t dt shall be equal to of course this is integrated over all time. Now, as I said, you see, sometimes we shall prefer to use angular frequency omega, sometimes we shall prefer to use Hertz frequency f.